In this presentation, I am going to explain single phase, half control and three phase control rectifier fed DC motor drive. Single phase half control rectifier control of separately excited DC motor. Therefore, here single phase half control rectifier that is given to a separately excited motor. That is the equivalent circuit, armature resistance, armature inductance, and the back EMF. Now, in a half control rectifier, as you know that one leg will be diodes D. Here which is equal to D3 and D2, and other leg will be the thyristors. Here T1 and T4. Now, from omega t equal to alpha to pi, therefore this is the input voltage, and from omega t equal to alpha to pi, thyristor T1 and diode D1 are conducting. Then here thyristor T1 and D1 are conducting, and the voltage VA is same as Vs. That will be getting the output voltage same as Vs. And that is for it, and the T1 and D1 and are conducting. Armature voltage equal to Vs is same as the source voltage Vs, and the source current Is is same as the load current. Here the source current will be same as the load current. Whatever this load current is same as source current is same as that one. Now at omega t equal to pi, that is at this instant at pi, the diode D2 is forward biased, because here the polarity of the voltage become positive here. Therefore D2 gets here, not D2, D3. The diode at omega t equal to pi here, here T1, D1, D2 and T2, it is marked like that one. That is why this is equal to this diode. This diode is getting forward biased. As this is getting forward biased here a reverse voltage comes across the SCR, which is already in conduction, that will be getting turned off. Therefore, as the diode D2 is forward biased and it starts conducting, at the same time instant T1 is turned off due to the reverse voltage that is applied by the source through the diode D2. Through the D2, the reverse voltage is applying to this one, that is getting reverse bias. Therefore, that is getting turned off to D2. When then D1 and D2 are conducting. After that one, that is after pi to next pi plus alpha, these diodes are conducting. That is diodes D1 and D2 are conducting. The diodes D1 and D2 are conducting, and that is called the freewheeling action is taking place. There will be a current circulating this one, and the voltage across this one is equal to 0, because we are assuming that diode drop is negligibly small. That is why the drop VA, the voltage across the armature equal to 0, and there will be a current through the motor. That is the current through the motor. This is a continuous conduction case. We are considering a continuous conduction case. There will be a current continuously through the motor, and during that period, since there is no current from the source side, source current is equal to 0. Therefore, at that is reverse the voltage and applied by the current diode. And when diode D1 and D2 are conducting the freewheeling, armature voltage VA is 0 and the source current Is is also 0. That is armature voltage equal to 0 and source current equal to 0 from pi to pi plus alpha. Therefore, at pi plus alpha, we are triggering the second thyristor T1 and then T2, and then T2 and D2 will be conducting. Then T1, T2 and D2 are conducting. Then you will be getting here again this voltage minus Vs is coming until next here 2 pi, and that will be repeating like this. Again after that one there will be 0 current. Therefore, this is the output voltage or the voltage across the armature in the case of continuous conduction mode of a single phase half control rectifier. Single phase half control rectifier for DC motors. As I already explained, this is the waveform, output voltage, and this is the current through the motor, load current, and this is the source current. and the different thyristors that are conducting, that is from alpha to pi, we are getting T1 and D1 are conducting. T1 and D1 are conducting. And from pi to pi plus alpha, D1 and D2 are conducting. It's called the freewheeling operation. D1 and D2 are conducting. At pi plus alpha, that is at omega t equal to pi plus alpha, T2 is turned on by applying a triggering signal, triggering pulse to this T2, and D1 is automatically turned off. And during omega t equal to pi plus alpha to 2 pi, armature voltage VA equal to minus Vs and the source current IA equal to minus IA. Therefore, the source current will be minus IA and the voltage will become equal to minus Vs. Therefore, this is the output voltage. And during that period, from this to this one, you'll be conducting the correspondingly T2 and D2 are the devices, or the thyristor T2 and D2 the diodes are conducting. Again from this one 2 pi to again 2 pi plus alpha, that is during this period D1 and D2 are conducting. That's called freewheeling, and that will be continuing. And in this case, the average output voltage, that is average output voltage equal to 1 by pi integral alpha to pi Vm sin omega t d omega t, or Vm by pi into 1 plus cos alpha. Whether if you are making the alpha equal to 0, you'll be getting 2 Vm by pi. When alpha equal to pi by 2, you'll be getting Vm by pi. When alpha equal to pi, you will be getting 0 voltage. For always the voltage across the armature will be positive. Therefore, you will be getting only positive voltage across the armature. Therefore, similarly, the current is also in this direction is possible. Therefore, that can be made to work only in the first quadrant operation, or forward motoring operation. It can be used. Previous slide I explained the continuous conduction mode. In this case, single phase half controlled rectifier per DC motor in discontinuous conduction mode. Therefore, there will be during that current is not continuous, that is coming to 0, and then there will be 0 current duration, and then what is the corresponding voltages? Let us see that one. From omega t equal to alpha to pi, that is from omega t equal to alpha to pi, thyristors T1 and diode D2 are conducting, as we have already seen. They are conducting, and the output voltage VA is same as the source voltage Vs, and the source current IA is same as the load current. That is from alpha to pi. That is during this period, similar to the previous one, it is equal to Vs. Now at pi here, that is at omega t equal to pi, diode D2 is forward biased, and the thyristor T1 is turned off due to the reverse voltage. As we already explained, this will be forward biased, and that will be applying a reverse voltage in this T1, and that is getting turned off. Then what T1 and D2 are conducting, that is during this period, here you can say that D1 and D2 are conducting, and that will be this due to the inductive energy as well as the energies because of the back EMF that is already there, and there will be a circulating current through this one, and that current will become flowing through this freewheeling diode, and the voltage will become 0. During that period, the voltage equal to 0. Turned off and turned off. During omega t equal to pi plus beta, that is, this is called the beta mode. Pi plus beta, both diode D1 and D2 are conducting and the freewheeling, and the armature current VA is same as the source current. Armature current VA and the source current will become equal to 0. At omega t equal to beta, that is at omega t equal to beta, at this instant, at omega t equal to beta, armature current decreases to 0, and both diodes D1 and D2 are reverse biased, and hence during omega t equal to beta to pi plus alpha, all the devices are turned off. That is during that period, during this period, all the devices are getting turned off, and none of the devices are conducting here. Then the output voltage, this armature voltage, that armature voltage is same as back EMF, because already the back EMF is there, because motor is running, the field is there, therefore back EMF is coming here. That is why after that point, the voltage is equal to back EMF is up, that will be there until pi plus alpha, that is that's beta to pi plus alpha. All the devices are turned off. Since the armature current is 0, armature voltage is same as the back EMF, that is armature voltage during that period, that is equal to back EMF. Continuing the discontinuous conduction mode of single phase half control rectifier for DC motor. At omega t equal to pi plus alpha, that is at omega t equal to pi plus alpha, T2 is turned on by applying a firing pulse from omega t plus pi plus alpha to pi, that is from pi plus alpha to pi. During that period, thyristor T2 and the diode D2 are conducting. Similar to the previous case, thyristors T2 and D2 are conducting and armature voltage VA is equal to minus VS. That is, armature voltage is VA equal to minus VS. Now, and similarly, the source current IS is equal to minus IA. During that period, the source current is equal to minus IA. Therefore, this is the plot of voltages, armature current or the load current and the source current and the different devices that are conducting. Here T1, D1, then D1, D2, none of the devices are conducting. T2, D2, D1, D2, none of the devices are conducting, like that. Or what are the devices are conducting for different durations, that is represented by this graph. And the average voltage in the case of a discontinuous case, average voltage is given by this equation 1 by pi integral alpha 2 pi Vm sin omega t plus here we can say that during this period, that is beta 2 pi plus alpha E d omega t, and then you will be getting, this is the equation for the voltage that is coming across the armature. In terms of beta also, this is the voltage across the armature. Now corresponding equations for the torque equal to, as you know, that K into Ia, and similarly back EMF equal to K into omega m. From this one you can calculate what is omega m, E by K, where E equal to VA minus IARA divided by K. And this VA can be, that is whatever the VA calculated, this one, that can be substituted here, and then you can get what is the omega m, what is the relation between omega m and the torque. The speed torque characteristic is given, and here omega m is calculated, that is reduced here, and then omega m is calculated here, Vm into 1 plus cos alpha divided by K into beta minus alpha minus pi into Ra divided by A square into beta minus alpha into T. This is the equation for speed torque equation for a separately excited DC motor fed from a single phase half control rectifier in discontinuous conduction mode. For beta, we don't know what is the beta. It's a function of beta also. Coming to a three-phase fully controlled rectifier fed separately excited DC motor. And here under continuous conduction, each thyristor conducts for 120 degree. At any instant, two of the thyristors will be conducting. Therefore, this is a circuit diagram of a three-phase fully controlled rectifier fed separately excited DC motor, in which three-phase supply is given, and there are 6 SCRs and 3 legs. In each leg there are 2 SCRs, T1, T2, T1, T3, T5, T2, T4, T6, and here at any instant each thyristors are conducting for 120 degree, and at any instant 3 SCRs are conducting, maybe 2 from the top and 1 from the bottom, or maybe 2 from the bottom and 1 from the top. Depending upon the SCRs which are conducting here, the voltage across the armature will be changing. Whatever the lines they are conducting, that will be the line voltage. That line voltage will be coming across the armature. Therefore, a three-phase case, one thyristor from the upper group and other 2 from the lower group, or then the reverse case also can be possible. And the thyristors are fired in the sequence of their numbers. That is, first T1 is fired, after 60 degree T2 is fired, after 60 degree T3 is fired, then 60 degree T4, again 60 degree T5, again 60 degree T6, then again 60 degree T1. For the firing sequence is T1, T2, T3, T4, T5, T6, and each device are conducting for 120 degree duration. You can see that each device are conducting for 120 degree duration, and the firing sequence is in this order. And based on this one, you will be getting the output voltage, and you can find out the average output voltage that is coming across the armature. That's a function of firing angle, and this is the line voltage that is representing. That is a shifting, because line voltage will be shifted by 30 degree from the phase voltages. So VAB to get, for example, VAB equal to VAN minus VBN, and that will be 30 degree shifted. Therefore, that is how the line voltages are there. That is marked as a phasor diagram here. This is the phase voltage and this is the corresponding line voltage. We are calculating the line voltage like as I already explained. VAC means VAN minus VCN. Similarly, VAB equal to VAN minus VBN. Like that one, we are calculating the phase voltages, and depending upon the phases that are conducting, you will be getting that voltage phase line voltages. These are the line voltages. Depending upon the phases that are conducting, the line voltages will be. This is the line voltage and this is the phase voltage, and these are the devices that are conducting for different durations. In three-phase control rectifier, average output voltage can be changed by controlling the firing angle. Now let us calculate that one. The average output voltage of a three-phase fully controlled rectifier can be derived like that one. For example, the voltage VA equal to Vm sin omega t, VB equal to Vm sin omega t minus 120 degree, or VAB equal to root 3 times Vm sin omega t plus 30. This is the line voltages. Now the armature current is assumed to be continuous and the average value of the output voltage can be calculated. Average voltage is given by 6 divided by 2 pi into root of pi plus 30 to pi plus 90 root 3 Vm sin omega t plus 30 d omega t. Here there will be 6 humps like that one, 6 humps, or in each one has a 60 degree. That is why in a 1 2 pi radians, one cycle, there will be 6 such humps are there like this performance. Therefore, that is why here 6 times it is written 6 into whatever that root 3 Vm sin omega t plus 30, that is spread over 2 pi. That is why 6 divided by 2 pi integral alpha plus 30 to alpha plus 90 root 3 Vm sin omega t plus 30, and that is 6 root 3 Vm divided by 2 pi minus cos omega t plus 30, and you are substituting the limit alpha plus 30 plus alpha plus 90, and substituting that one in this equation here, you will be getting 6 root 3 Vm divided by 2 pi into cos alpha plus 60 minus cos alpha plus 120 degree, and again substituting the cos, expanding that one, that is cos alpha plus 60 can be written as 90 minus 30, and 120 can be written as 90 plus 30. Therefore, same 6 root 3 Vm divided by 2 pi into cos alpha plus 90 minus 30 minus cos alpha plus 90 plus 30. And here substituting here, it is equal to cos a minus b minus cos a plus b equal to 2 sin a sin b. Therefore, cos a minus b minus cos a plus b equal to 2 sin a sin b. Substituting that one here, 6 root 3 Vm divided by 2 pi into 2 sin alpha plus 90 into sin 30 degree. That is, we are substituting this equation 2 sin a sin b here, and substituting that one, you will be getting the average voltage in the case of a three-phase control rectifier equal to 3 VML by pi cos alpha, 3 times maximum line voltage divided by pi into cos alpha. Therefore, by controlling the firing angle alpha, you can vary the average voltage across the armature. In other case, that if alpha is less than pi by 2, you will be getting a positive voltage. If alpha is more than pi by 2, you will be getting a negative voltage. That when alpha is less than pi by 2, it can work as a rectifier. When alpha is more than pi by 2, it can work as a inverter. Therefore, Vm is the peak value of the phase voltage. And VML is the maximum value of the line voltage in the peak value of the line voltage. Now, once get the average voltage across the armature is equal to 3 VML by pi cos alpha, then corresponding equation for omega m can be torque equal to T equal to K into Ia, back EMF E equal to again K into omega m equal to E by K. Then substituting for this one, you will be getting it is equal to 3 VML by pi cos alpha by K, that is 3 VML cos alpha divided by pi K minus Ra by K square into T. Therefore, this is the speed torque equation for a three-phase fully controlled rectifier but separately excited DC motor, and the average value is given by 3 VML by cos alpha. Therefore, by controlling the value of the alpha, the average value of the average values voltage across the armature can be changed. Coming to a problem, a 220 volt 1500 rpm 50 amperes separately excited DC motor with Ra equal to 0.5 ohm is fed from a three-phase fully controlled rectifier and available AC source as a line voltage of 440 volt 50 hertz, and a star delta connected transformer is used to feed the armature so that motor terminal voltage equals to the rated voltage when converter firing angle is equal to 0. Calculate the transformer trains ratio, first one. Second, determine the value of the firing angle when motor is running at 1200 rpm and the rated torque when motor is running at minus 800 rpm and twice the rated torque. About the three parts are there. Let us see first one, solution. For a three-phase fully controlled rectifier, as already we derived, it is the average voltage equal to 3 VML by cos alpha. Now here, corresponding to alpha equal to 0 degree, you are getting the rated voltage. For 220 volt is the rated voltage. That 220 volt you are getting corresponding to 3 VML by cos alpha equal to the rated voltage. Therefore, substituting that one, that is that voltage here, 3 VML by pi cos alpha into cos alpha equal to 0 degree. It is equal to 0 degree, and you will be getting what is the maximum line voltage. That is VML is given by 220 divided by cos 0 into pi by 3, or it is equal to 230.4. The maximum line voltage of the secondary it is a the transformers available source voltage. It is a fully controlled rectifier. It is a star delta transformer. Therefore, in delta side, the maximum line voltage is equal to 230 volt, and in order to it is equal to Vm by cos alpha, this is pi by 3, and the RMS value of the line voltage is given by, this is the maximum of the line voltage, and the RMS voltage is given by 162.9 volt. This is the RMS voltage at the secondary side, the delta side, say star delta transformer. Secondary side, the RMS value of the line voltage, and the RMS value of the voltage at the primary side is given by, it is equal to 440 volt. Therefore, for RMS value of this, it is a this is the RMS value of the line voltage, and for a star connected connection, the ratio of the turns between the phase the phase winding of the primary secondary, this is the per phase voltage in the primary side, 440 divided by root 3 divided by, since the delta connected, per phase line voltage and phase current phase voltage are same, it is equal to 162.9 volt, and therefore the turns ratio is equal to 1.559. Therefore the turns ratio of the star delta transformer should be 1.559. Second part is at 1500 rpm, back EMF equal to, as you know, it is equal to VA, that is 220 minus IARA, it is equal to 195 volt. This is the back EMF. Is at the rated speed, this is the back EMF. Now at 1200 rpm, the question, that's 1200 rpm, corresponding back EMF can be calculated. 195 divided by 1500 into 1200 is equal to 156 volt. Therefore, this is the back EMF corresponding to 1200 rpm. Now, what should be the required armature voltage VA is given by, this is the back EMF 156, that is E plus IARA. 156 plus IA is same the rated torque, therefore it is equal to 50 into 0.5, it is equal to 181 volt. The voltage is equal to 181 volt is the armature voltage. Now the equation armature voltage and line voltage 3 VML by pi cos alpha, or cos alpha is equal to, you can get it is equal to VA into pi divided by 3 times VML. Substituting this one, you will be getting what is alpha. Therefore, cos alpha is equal to VA the average voltage is calculated as 181 volt, and the average voltage VA is related by 3 VML by cos alpha, where cos alpha equal to VA into pi divided by 3 VML. From this equation, you can find out what is the cos alpha or alpha. For cos alpha equal to VA equal to 181. 181 into pi divided by 3 into 230.4. That's equal to 0.8227. Or alpha equal to 34.65 degree. The last part of this is at 800 RPM, corresponding back EMF equal to 195 divided by 1500 into minus 800. Minus 800 RPM is equal to minus 104 volt. In the same manner, you can find out what is the armature voltage corresponding to this back EMF. Therefore, that is equal to, you will be getting it is equal to minus 54 volt. That is the back EMF. Now you can, corresponding to this one, back EMF is this much, and this is the armature voltage. Minus 54 volt is the armature voltage. Now to get this much armature voltage, minus 54 volt, what should be the firing angle? Cos alpha, or what should be alpha? For the cos alpha is again given by minus 54, that is here. Minus 54 into pi divided by 3 times, it's equal to the maximum line voltage. It's already 230.4. You will be getting minus 0.2454, or alpha is equal to 104.2 degrees. Therefore, this is the firing angle corresponding to the third phase, minus 800 RPM.